complex numbers, simple explanation. Let's get started. The complex number is usually just I. That's the main part of complex numbers. So I. And I is equal to square root -1. Now obviously square root -1 usually doesn't exist because you can't actually square root a negative number. But in the complex world, it does exist, and that's where things get a bit interesting. So from this I is equal to square root -1, we can also know that I squared is equal to -1, because square root -1 squared will just remove the square root and become -1. And I to the power of 3 is equal to -I, because you have your I squared, that'll be -1, and then square root -1, which is just negative I, which could also be said to be negative square root -1. That just gets a bit hard to say. I to the power of 4 is equal to 1, because you got your I squared, -1 times -1, which will give you 1. So I to the power of 4 is 1. Now you can obviously keep on going past that, so you can get I to the power of 5. Actually, yep, I to the power of 5, which is actually just equal to I, because it'll be 1 times I. Don't know why I didn't write that in the thicker pen. Just be equal to I. And then past that, there is further patterns, but in reality, you don't really need to know past I to the power of 4. Like, it's usually not going to help you knowing that far ahead. I'll quickly just rub this out, but this is kind of the basics that you want to know. Now, when you get given a complex number, it'll likely be in this form. So it'll be when Z is a complex number, it'll be Z is equal to A plus BI, where A and B are real numbers. Now, A, that's said to be the real part of this complex number is A, as it doesn't have the I next to it. It's just a normal number. So our real value in Z is equal to A, whereas there's an imaginary part within this number as well. So imaginary part of Z is equal to B. Now, as you can see, you can almost consider it a linear, but it's far from a linear. It's sketched on a different graph, which is called Argand diagram, where you have your real axis and your imaginary axis, where any point, let's say here, is AB. Now, there's multiple different forms you can have complex numbers in, which will be discussed later, where you could also encounter rings around the Argand diagram to help sketch, but we're not going to be going over that yet. So a complex number is sketched on a graph that looks something like this. But now we're just going to go over the basics of how to add, subtract, divide, and multiply, which is also relatively simple. So as you can see from this, Z, which is the complex number, is equal to A plus BI. Therefore, if you want to plus another complex number, so I'm just going to call that, I'm just going to call that Z1 or something, and we'll make that equal to D plus C. Actually, I should probably do the C first. I'll make that Z1 is equal to C plus DI. And then we'll just calculate Z plus Z1. Now, this will just be equal to A plus BI bi, and then plus c plus di. And when you're adding complex numbers, if there's a real and an imaginary part, which there is, you can only add them to their own part as such. So we're going to add our real numbers, which is a plus c, for those in brackets, they're our real numbers, and then we can add our imaginary numbers, which is b plus d I. And this is just the total, this is just an expanded, I don't even know what to call it really, but z plus z1, you can get a rule. You plus two complex numbers together, you end up with this rule here, where you have to plus the real numbers together, and then plus the imaginary parts together. And that's pretty much it. Subtraction's literally just the same. Z minus Z1, you end up just getting A plus BI, which is your Z, and then subtracting Z1, which will be minus C minus DI. You've got to remember to apply the negative to the whole term. And then you'll get A minus C, that's from subtracting your real parts, and then you'll get B minus D from subtracting your imaginary parts. And that's pretty much as simple as it gets. I will just do one quick example with numbers, just so you can actually see what it looks like. So we'll just go, we'll just let Z3, which is a complex number, equal to 5 plus 6i. 5 plus 6i. And then Z4 can be equal to 3 minus 7i. Now if you plus these two together, which will be Z3 plus Z4, you'll have to plus your real parts together, which will be 5. Actually, we'll just quickly expand it. Well, we'll just quickly show what it's going to be equal to. So Z3 will be 5 plus 6i, and then it'll be plus Z4, which is 3 minus 7i. That's a really thick dot on the top there. And then you have to plus your real parts together, which will be 8. And then you have to plus, which you end up subtracting, but then you just have to add together your imaginary parts, which you'll end up with, so 6i minus 7i will just be minus I. And then that'd be your answer for that question there. And that's pretty much for the addition and subtraction. Now I'll quickly go over the multiplication, which is pretty simple. It's just similar to a normal quadratic. Looks like it's going to end my page there. We'll keep the same examples. So we'll have Z1, which is equal to, I'm just going to go, actually, that wasn't it, I don't think. Oh no, yeah, it was. I skipped Z2. A plus, so Z is A plus BI, and then Z1 is equal to C plus DI. Now we're going to go Z multiplied by Z1. We'll make that a multiplication sign. And then just inserting our values, we'll have A plus BI times C C plus di. Now you can pretty much just use your normal expanding method to get the answer. It's not too complicated. So we're just going to go and do that. We got a times c, so that'll just give us ac, a times di, which will be a d I, and then we got bi times c, so plus c bi, and then our final part where we got bi times di, which will give us plus b d, and then the multiplication of the i's. So we're going to go, that is going to end up being I squared. Pick the wrong pen again. It's going to end up being I squared. Yep. I'm not sure if I rubbed it out. Yeah, I did rub it out. But just from what we did previously, we remember that I squared is just -1. So we can simplify this further to be AC plus ADI plus ADI plus CBI plus BD, and then the I squared, which is -1, which doesn't result in a plus, it results in minus BI, minus BD. So therefore this number here has been turned into a real number. So then we can collect our real numbers and our imaginary numbers, and then you'll get AC plus BD, and then plus AD plus CBI. That's pretty much as simple as it gets. Alrighty, then next we'll do division, which is pretty much just the same thing again. So scroll up just one bit. There we go. So we'll evaluate Z over Z1. Z1. And with the division, you have to use a slightly different method, which I'll go over in just 1 second. So we can write this as Z, which is A plus BI, over Z1, which is C plus DI. Then to actually simplify this further, you do something where you have to multiply this entire fraction by the conjugate of Z1, which is your denominator. And the conjugate of a complex number is literally just changing the sign next to the imaginary part. So our conjugate of Z1, so if Z1 is equal to, which it is, C plus DI, our conjugate, which is denoted by a line on the top, is going to be equal to C minus DI. And it's as simple as that. So you multiply this by C minus DI over, well, and then, sorry, C minus DI on top, and then over C minus DI, which in reality is equal to 1, because that's just how it is. And then you get this is equal to, this is a difference of perfect squares, or a difference of 2 squares, which normally it would just be c squared minus d squared, but due to the complex number I, due to I being squared, it turns the second term into a plus. So instead of c squared minus d squared, it is c squared plus d squared. So we can write that on the bottom, c squared plus d squared over a plus bi, c minus di, which we actually have the expanded version down here, but we don't actually need to write the expanded version. Oh no, that's actually not the expanded version, because we got the conjugate. And then that's it there. We'll just quickly expand the top though. So you get AC minus ADI plus B plus CBI, and then you'll get plus, you'll be plus BD. And then you can combine your like terms of, which will be, you combine your imaginary and real paths. So we'll have AC plus BD, and then you'll have, I don't even know what I've done there. BCI. So then you'll have BC, sorry, I need the plus BC minus ADI. And I'm pretty sure that's it. And I'll just do a quick example using these steps here. We'll just have, we'll just restart our z's. We'll just let z be equal to 3, so z is an element of a complex number. Z is equal to 3 plus square root 2i, and then z1 equal to square root 5 minus 6i. It is common with complex numbers to be given square roots in them. Don't know why. Actually, I don't know why. It's when converting them to polar form, you get like clean radians. I'd assume that's why. That's actually just a made-up definition. So we can multiply these together. We'll have z times z1, which is just expanded normally. So insert the values you have here. Square root 5 minus 6i. I'm going to stop doing the bold because it's slowing me down. You have 3 square root 5. And you have minus 18i. And then the next term will be square root 3 plus square root 5, which will be square root 15. So plus square root 15i. And then you have square root 3 times the negative 6i, but with the I squared, which will turn into a, so without the I, I'll just quickly do something. Timesing this together, you get 6 square root 3 I squared, and the I squared we know is negative 1, so then we can rewrite this as plus, and there you go. or combined are like terms of real and imaginary parts. Square root 3 square root 5, and then 6 square root 3. Then we'll just do plus square root 15 minus 18i. And it is as simple as that. Now we'll just do a quick division of this one, which hopefully shouldn't take too long either. We'll have z over z1. Right. 3 plus square root 2i over square root 5 minus 6i. And then our next step is to multiply by the conjugate of the denominator, and which will just be equal to 1 because you do times the numerator by the conjugate and the denominator by the conjugate. Multiply by square root 5 plus 6i over square root 5 plus 6i. And then, yeah, we can use I guess we kind of have a formula written above here. You could kind of use this formula, but you can pretty much just do it by, like, on the roll as well. You don't really need to use the formula. You can just use general algebra. So here we got that difference of two squares situation. So we'll have the 5 times the 5, square root 5 times square root 5, which will just be 5. And then the negative and the negative 6 and the positive 6, which will usually form 36. Negative 36 is kind of cancelled out by the I squared, which will turn into a plus. So that's what we've got on our denominator. We will simplify that in the next step, but we'll just expand what we have up here first. So we have 3 square root 5 plus 18i plus square root 10i, and then minus 6 square root 2. And we'll fully simplify this now. No, maybe not fully, but we'll simplify. And 3 root 5, so we'll plus the real parts, minus 6 root 2, and then plus 18 plus root 10 I. I'll make that bold again. And there you have it, which could also be equal to yeah, you could obviously like go the real parts over 41 and the imaginary parts over 41, which I guess we'll just do. And that's pretty much it. That'd be your basic complex numbers and how to multiply, divide, subtract, and add them. That's it.